Hey everybody, welcome back to AIT 1003. We are going to keep rolling on. We've got just a little bit more to talk about. Your book has an example in here I thought would be good to work through on this lecture. And then I got a little bit to talk about on gauges, and we'll wrap this up as far as the lecturing goes on lesson 2. So let's jump right into it on your example in the book. Okay, let's work through it and maybe help you out. First of all, it tells us we're going to move a 25-pound wedge. It's kind of like a log splitter. And the wedge weighs about 25 pounds. And we've got a piston diameter of our hydraulic cylinder of 2 inches. Okay, so we know how to figure out the area. Okay, it's the area of the extend side of the piston is going to be pi times the radius squared. Okay, first of all, the radius is what? Half the diameter. So our diameter is 2 inches. What's half of 2? 1. Okay, so we square 1. 1 times 1 is 1. And we multiply the radius squared times pi. All right, and we wound up with 3.146 times 1, which is 3.146 square inches on the extend side of the cylinder for that 2-inch cylinder. That's the surface area we have on the extend side. Okay, so again, we've got our formula, and so we have our extend side surface area of 3.1416. Okay, we have a force. We're trying to move a 25-pound wedge. We divide that by our area on the extend side, and we wind up requiring a pressure of 7.95 or 8 pounds per square inch from our pump. We need our pump to deliver a minimum of 7.95 or 8 pounds per square inch to move that 25-pound wedge with a 2-inch cylinder, because the 2-inch cylinder is going to give us 3.1416 square inches of pushing surface on the extend side. Okay, now what about the other thing we have to do, though, is we have to consider we got to pull that 25-pound weight back. Okay, we've extended it, and we know what's required to extend it, but what's required to pull it back, because we also have to pull it back, and it's still that same 25-pound weight. All right, we said in our previous video that we've got to take into account the rod diameter, or the surface area of the rod that's taking up or taking away from the pushing area of the retract side of the piston. Okay, so we got to subtract that, because we don't get all of the surface area to retract with, because the rod is eating up some of that surface area. So here's how we figure that out. First of all, we said the rod diameter is 0.7 inches. Okay, it's just about 3/4 inch rod. All right, and so it's 0.7 inches. Okay, that's the diameter. So the radius would be half of that. Okay, so 0.7, half of 0.7 is 0.35. Okay, so we take our pi and we multiply it by our radius squared. We got to square our radius. That comes out to 0.1225. So we've got pi times 1.1225, and that gives us a rod area of 0.385 square inches. Okay, that's 0.385 square inches of rod surface area. Okay, now we know that from our previous example, or the previous slide, that we have an extend side square area of 3.1416 on the extend side. Okay, now we have the same amount on the other side, except for the rod's taking it up, so we got to subtract the rod away from that. So we take 3.1416, subtract the rod, which is 0.385 square inches, and then we have a retract surface area that's available for us to push against of 2.76 square inches. Okay, let's look at the contrast between those two. Okay, 2.76, and on the extend side 3.14. Okay, you're kind of seeing where this is going. But let's continue with this one. On the A sub retract, we have 2.76 square inches. Okay, now we still have the same 25-pound wedge that we're trying to pull. We're trying to move it. This time we're trying to pull it. Okay, we're actually trying to pull it with less surface area. So 25 divided by 2.76 is the square, is the area on the retract side. And we're going to need our pump to put out a minimum of 9.05 pounds per square inch in order to retract that 25-pound wedge with the 2-inch cylinder. Okay, so let's kind of summarize this real quick. The pressure required on the extend side down here to move that 25-pound wedge is going to be 7.95, almost 8 pounds of pressure from our pump. Okay, that's what we need from our pump. In order to retract that same 25 pounds, though, we're going to have more pressure because we don't have the same amount of surface area on here, right here, pressing down, because this rod is eating up some of that surface area, so we've lost surface area. So we've got to compensate and jack the pressure up, okay, in order for it to pull that 25-pound wedge. If we didn't change the pressures, if we had a system set at 7.95, it would extend it and it would not retract it. It would try, but it would stall, okay? So there's a difference of 1.1 psi that's required to get the cylinder to extend that wedge on the log splitter, as opposed to how much it brings back, or how much is required to bring it back, okay, which is 9.05 pounds per square inch. So you can kind of see the difference between that. Now, I left you with a previous thought, and that was if you had the same amount of pressure on the retract and extend side, what would your cylinder do? A lot of students will tell me it'll just stall. Now, that's not right. Actually, it will drift. The extend side will sort of slowly overtake the retract side because it's got more surface area to push against than the rod, so it's going to win the pressure battle there, okay, or the force battle. So anyway, that was just an example out of the book. I thought it might help you try to work through it. Very quickly, I want to talk about gauges. They're kind of important because gauges help us learn about the health of the machine. Also, if you're troubleshooting, if you don't have enough pressure, what's going on? Are we losing pressure? Do we have the ample pressure? If you got ample pressure, then we need to start looking elsewhere, okay? So it gives us an idea of what our pump is doing. Are we delivering the proper amount of pressure and flow to the devices to make them work? There are three types of pressures, and that's atmospheric, gauge, and absolute, okay? Your book goes into pretty good detail about this, so I thought I'd talk about it just for a second. The atmospheric pressure, you hear that word thrown around a lot. Atmospheric pressure is the amount of pressure or the amount of weight that the atmosphere is actually putting on the earth at sea level, okay? For example, and I saw this explained, I like the way this was explained to me one time. Atmospheric pressure, if we were to take 1 inch square cubes, okay, 1 inch square, and we were to stack them on top of each other all the way up to the atmosphere, which is roughly, I think the top of the atmosphere is, I think, about 600 miles roughly, something like that. But if you were to stack them up there, the amount of weight that they would weigh would be 14.7 pounds, okay? That's 1 inch squares for 600 miles straight. It sounds kind of strange, but it's a simple way of looking at it. And you're standing there holding it, it would weigh 14.7 pounds, provided that we were at sea level, okay, that day at the beach, okay? So we've written that, not in the mountains, okay? But if we're standing there, that's how many, with those amount of columns, those amount of squares going in a column right up to the atmosphere, it would weigh 14.7 pounds per square inch, okay, well, 14.7 pounds, okay? Actually, it's supposed to be 14.7, not 14.5, not bad. But anyway, you get where I'm going with this. So when we say that we have atmospheric pressure of 14.7 pounds, that's where it's coming from, okay? Now, we're subjected to this, our bodies are subjected to 14.7 pounds, and the reason our bodies are not caving in because of our the area, pressing all over our bodies, is we have an equal amount of force on the outside, on the inside of our body too. So the force is equalized, all right? Here's a little thing just kind of to tell you, for example, to kind of relate to the atmospheric pressure. You got atmospheric pressure pressing down 14.7 pounds per square inch. Now, I don't know what the surface area inside this cup is. We can figure it out now, though, can't we? But we can figure it out, and we multiply that by, instead of a pump pressure of 250 or 100, whatever, we would apply the pressure of 14.7 pounds to this, and that's how much atmospheric pressure is being pushed down into this glass in this cup. What happens when we put a straw in our mouth and we pull that liquid into our mouth, we are not so much creating suction or anything, but what we're doing is our mouth, I said the internal pressure is still 14.7, it's the 14.7 inside our mouth as well. And what we're doing, though, is we are lowering the pressure inside of our mouth to less than 14.75. Remember the cylinder I told you about that had on the retract and extend? If we put more pressure on the extend side, it's going to kind of win the battle a little bit because it's going to take the path of least resistance. The retract side has less force than the extend side, so it's going to drift. Sort of the same thing with this. We have 14.75 pounds of pressure going against this water right here. We have the same amount in our mouth. If we reduce it in our mouth, the force is going to be greater here, and it's going to force this liquid into the area that has less resistance, the path of least resistance, or lower pressure side, okay? And yet that's critical in the hydraulic world and fluid power world, is that it's going to go toward the lesser pressure. When we're drawing in, we're actually creating a condition inside of our mouth that is less than the 14.7 pounds the atmosphere is created. So the atmosphere kind of wins, and it shoves that water. It's really actually pushing the water. We're not sucking the water in our mouth. The atmosphere is pushing the water into our mouth. So it's a different way to look at it. So now you're kind of, just going to throw that at you a little bit. But that's how we get the water. We're not sucking the water in. We're dropping the pressure to less than atmospheric in our mouth, and the atmosphere is shoving that water, forcing that water into our mouth through the straw, okay? And again, we talk about sea level. Why is that important? Because remember the cubes, the cubes, the 1 inch square cubes stacked to the atmosphere? Well, if I'm down here at sea level at the beach, I'm going to have more cubes. I'll be holding more cubes than I would be in here, because that's the difference between here and here to the atmosphere. So the atmospheric pressure at higher altitudes is going to be less. You talk about some of the mountain climbers experience very light pressure, or very much less pressure up there in the mountains. Also, when you fly, the reason that planes have pressurized cabins is because the pressure is much less up there in the air, and so we have to compensate for the pressure in the cabin so that we could, live while we're flying in those high altitudes. So anyway, my point is it just give you some point of reference here is all it is. This is sea level versus mountain. So, again, the pressure is going to be less in the mountain because why? The amount of force from the atmosphere is less from here than it is here. You kind of picture those cubes. You'll be holding more cubes from here to here than you would be to get to here to there. Just kind of putting it into perspective for you, okay? When it comes to gauges, though, that's what we're really concerned about. When it comes to gauges, there's a couple different kinds of gauges. But the one you'll see most often is the pressure gauge the gauge pressure, excuse me. And by gauge, what I mean is that it is taking into account the 14.7 pounds of atmospheric pressure. It's reading zero. It's sort of somewhat calibrated so that it's the 14.7 sort of moved the dial to a zero, okay? It's still experiencing the 14.7 pounds of atmospheric pressure on the gauge, but we've set the dial to where it reads zero, and that is gauge pressure, okay? Now, that's opposed to absolute pressure. Absolute pressure is the atmospheric pressure, which is 14.7, plus anything that the gauge reads. Those two combined create an absolute pressure. So while we have, let's say your gauge reads zero right here, okay? And let's just say it reads, I think I've got another example right here, okay? So we have a gauge pressure of 100 psi-G, which is designated, the G stands for gauge. So we got gauge pressure, our little dial is up at 100 psi. Okay, that's gauge pressure. But what it's not showing you is it's also taking into account the atmospheric pressure of 14.7. So between the gauge pressure and the atmospheric pressure, we have what's known as absolute, and that takes both of those. So our absolute pressure between these two is actually 114.7, because you add 100 pounds plus the known 14.7 atmospheric pressure at sea level, and then you wind up with 114.7 absolute pressure. So I wanted to give you a point of reference to that. And again, this helps us as far as troubleshooting and knowing what we are actually reading, because vacuum plays in inches of mercury, which is a negative pressure, but it's still considered a pressure. That all comes into play when it's time to troubleshoot, which we'll get into in some of the additional classes. But for right now, that's going to take care of things. And again, if you've seen anything in these lecture videos for this lesson that's not coming clear to you or anything like that, come see me and we'll talk about it, okay? And other than that, thanks for watching. We'll see you in the lab, and I appreciate your attention.